A cylinder is inscribed in a right circular cone of height 3.5 feet and radius at the base equal to 7 feet. The volume of a right circular cylinder is that, and here's the picture. Find the formula for the volume of the cylinder in terms of R only, not H. Okay, so basically, look, we got this cone, right? And we're trying to stick a cylinder, which is kind of like a soda can shape, inside of it. And really, excuse me, what we want to be able to figure out is what is the biggest, meaning hold the most volume, cylinder we can inscribe, it's called, we can put inscribe inside that cone. Meaning you could make it really tall and narrow, right? Where it's gonna hit the top. It's gonna go from the ground and it's gonna come up and hit the edges of the cone. You can make it this way. You can make it come up higher, but it'd have to be thinner. That probably is not gonna have more volume. You can make it a little wider, but then it's gonna be a little shorter, isn't it? Like more like a tuna can. So the question is where in between a short, wide tuna can shape, right? And a tall, thin tennis ball can is the best shape that'll have the most volume. That's really what we're trying to do. Now, this is only part one, so we're only going to do the setup. We're not going to actually find the final answer. We're not going to find the final radius that is the best to make the biggest cylinder fit inside that cone. That'll be part two. We're just going to do the setup here. So the setup is find the formula for the volume of the cylinder in terms of R only, not H. And then once you have that, you'll take this will be the volume, and you take the derivative, set it equal to zero, and you solve for the radius that maximizes the cylinder's volume. Anyway, we're just going to do the setup. How do we do it? How do we get the volume of the cylinder? Well, here's the volume. Let's just start right there. The volume is pi r squared h. You think, well, we're almost there, except they just said R only. They want the volume of the cylinder, R only, not H. So we just got to get rid of that H, right? Just somehow plug in for that H. How do we do it? Well, we know that there's a relationship that exists here. Let me show you right here. See this right here and that right there. See that triangle, that blue triangle? Well, inside of that blue triangle, we could put a purple triangle. You see there? Maybe I should make it red. Can you see that? Yeah, let me make it red. There. Yeah. See, those are similar triangles. Those are similar triangles. Let me just draw it right here. So let's see. Okay, so you know you got boom. Oops, that's not what I wanted to do. And then boom, and then boom. We get the outside shape, and then within it, we get this thing. Boom, boom, boom. All right. So we got a triangle inside of a triangle, don't we? And what we know is the this right here, this is the height of the whole cone. And it says the cone height is 3.5. So we just go, oh, okay. That's 3.5 from there to there. Okay. And it says the um, radius, this is again cone radius is 7. Well, see the R right there? That's the radius, right there. That's the radius. So this is 7. Doesn't look like 7 the way I've drawn it, but whatever. Right, that's 7 because that's the radius of the cone. You tracking with me? Here's the cone. Here's the middle of the cone to the edge. That's the radius of the cone. This is the radius of the cone. Okay, so okay, great, we got that. All right, and so then we know that this is the height and the radius of the oh no, that's not the radius, is it? The radius is here. Huh. The radius, height and radius of the soda can, right? That the cylinder right here. Here's the radius of the cylinder. See it right there, that little R right there, the radius of the cylinder. and this is the height of the cylinder. Right? This is the height of the cylinder, the soda can. This is the radius. So the radius and the height. Tracking with me? I'll scoot this over a little bit. Whoops. Here we go. All right. Great. So what? Well, we have similar triangles. These triangles are, this is a small version of the big one. We call that similar triangles in geometry. How do you know they're similar triangles? Well, they both have a 90-degree angle, and they both have this lower right corner is the same for both of them. So if you have two angles the same, that means you have all three angles the same because remember every triangle holds 180. So they both have a 90 and they both have the lower right corner same. So that means this one and this one must also be the same. If you have all three angles the same, you're similar triangles, which means this is just a shrunk down version of the big one. If we take that small one and we expanded it, it would fit exactly on the big one. They're identical except for size. So these are similar triangles, is what we call it. Similar triangles, which means that they are identical, except different sizes. So they're not different shapes. They're the same exact triangle shape. If you expanded one of them or shrunk the other one, they'd fit right on top of each other perfectly. They are the same shape. Okay. So which means what? Which means the ratios of their sides are going to be equal, meaning I could take left over bottom of the big one, and that's going to equal left over bottom of the small one. Right here, how about if I do the colors to help that be more clear? So this is the small triangle, and this over here will be for the large triangle. Okay, so this is easy. This is 3.5 over 7, right? Left and bottom of the big overall large triangle. And that has got to equal the left over the bottom of the little one. Well, here's the left. That's H. Now, what's the bottom? Well, the bottom's actually right there. Oh, what's that? That's got to be 7 minus R. Do you see that? Because 7's the whole distance. This is R. So you take the whole thing 7, take away this little piece R, and you got 7 minus R. So now we can diagonal cross multiply. 3.5 times 7 minus R equals 7H, like that. And so if you distribute there, I don't know what you get. What's 3.5 times 7? I don't know. So I'm going to go to Desmos. 3.5 times 7. 3.5 times 7 is 24.5. So we get 24.5 minus 3.5 R equals 7H. And we're trying to solve for H so we can plug it in right there. So then divide by 7, divide by 7, divide by 7. 24.5 over 7, I don't know. Take that answer, divide by 7. Hopefully it's nice, isn't it? Yeah, it's back to 3.5. Nice. Back to 3.5. So this is 3.5, right? That's over this, 3.5 minus, and what's 3.5 over 7? That's a half. That's 0.5. You can, right? Because that's half of that. 350 is half of $7. R equals H. So there's the equation for H. So now we can plug that in right there for H. And so we get, let me bring it down here. We get volume equals pi r squared H, which is pi r squared, and then H is 3.5 minus 0.5 R. There it is. Yeah, they just wrote it like this. They basically just left it unsimplified, but it's the same thing. And you could type it in that way or this way. So you got the pi r squared in the front, pi r squared in the front, and then we just cleaned it up. They left it they just left the 7 sitting on the bottom and everything else sitting on the top. That's fine. So there we go. That's the setup. So what we would do on part two, what we will do on part two on another problem, so say, all right, now we have the equation for the volume of that. That's the volume of the cylinder, right? That soda can that's inside there. That's the volume of that. So now take the derivative and set it equal to zero to find the radius that'll make the biggest soda can that can fit in that cone. So we're just stopping here at the setup on this one. And there we go.